Okay, welcome to Physics 102. This is Conceptual Physics, and I am Dr. Raymond Rogers, and I'll be your instructor for this class. I will have a brief walkthrough of the syllabus as well as my Blackboard course up on Blackboard. It'll be in the announcement section, but just want to keep those kind of separate from my lecture. I do like to just talk about basic expectations. Attend lectures. This is not a fully online class, so you probably actually want to go ahead and watch the lectures. You can watch those at 1.5 to 2x speed just to digest them a little bit faster. That's kind of the way I prefer my YouTube. If something doesn't make sense, feel free to ask. With mechanics in Physics 101, a lot of times things kind of made intuitive sense. But in Physics 102, we're actually going to be talking about some things that you can't really see or touch or feel, like magnetic fields. And so there are no stupid questions. Of course, do the work. The only way to get good at doing anything is to actually do it, and that's true of physics or baseball or basketball or football. And last but not least, do try to have a little bit of fun as we go through the course. I do always like to show Dale's cone of learning, and essentially it says, what do people take away from what they do? And you only take away 10% from what you read and 20% from what you hear, and only 30% from watching a video or something like that. And that's what actually makes what I think makes online learning kind of hard. I took an online photography class, and if I'm only taking away 30% from passively sitting there, that's kind of a bad thing. And as I said, photography was hard. So 50% of what you see, why do I say take notes? Why do I say write things down? It's because you take away more from it, and especially working through hands-on activities. And lastly, you take away about 90% of what you do. And the only way to get good at doing anything is to actually go ahead and do it. So with all that said, let's dive right into Chapter 19. We're going to be talking about waves, and I'm just going to be getting some jargon out of the way. First, I'm going to start off about talking about pendulums and wiggles and waves, and just getting some wave jargon out of the way. We'll talk about two types of mechanical waves. We'll talk about transverse waves and longitudinal waves. And then I'm going to say that waves can superimpose. They can live at the same place at the same times, and they can constructively or destructively interfere with each other. I'll talk about one special case of waves interference. I'll talk about standing waves, and I'll kind of finish up by talking about the Doppler effect as well as shock waves. So first I just want to kind of distinguish between a vibration and a wave. Something that is vibrating is just kind of wiggling in time, or you could even say in one-dimensional space. Something that's wiggling in both space and time, and I'll kind of distinguish that to be a two-dimensional space in time, is going to be a wave. And essentially it's going to go from one place to another. Waves are very, very good at transmitting energy. And what they can do is they can transmit energy from one place to another place. Some examples of waves might be a light wave, which is actually an electromagnetic wave, and that's a special type of wave because it does not need a medium, or it doesn't need something in order to be there for it to propagate. Sound is actually a mechanical wave, and it's going to need a medium. It's going to need some air or something like that. Light can go through outer space. Sound cannot. So just to kind of graphically see what's going on, if I had, say, an antenna, and I had an electron on that antenna, and that electron was just kind of wiggling up and down, so in one-dimensional space and time, then I would just say that electron was vibrating. But what it actually produces is going to be this guy right here, and that's going to be a wave, something that's wiggling in two-dimensional space and time. And what it's doing is it's transmitting energy from, say, the cell phone tower to, your cell phone, so you can, play games and stuff like that. So let's just talk about a pendulum really quick, and we're just going to have a pendulum that's vibrating in space, and it is kind of vibrating in two-dimensional space, but we'll just call it one-dimensional space and time. It's going to swing back and fro at a certain rate, and that rate is actually going to depend on the length of the pendulum and the length of the pendulum only. It's not going to depend on how massive it is. So if you've ever seen an adult and a kid sitting on a swing and the lengths are the same, then essentially they're going to go back and forth at the same rate because mass really doesn't matter. This is actually just kind of like falling balls. If you remember from Physics 101, when we dropped a heavy ball, or if we dropped a light ball, then they both fell down at the same rate. They accelerated at the same rate, 9.8 meters per second squared. Now, we do have a special name for how long it takes to go to and fro, and it's going to be called the period. Sometimes you're going to see that with a capital T. And of course, I always do stress the units. The unit for period is going to be a second. So you're going to say this pendulum is vibrating with a period of half of a second. And again, the longer the pendulum, the longer the period is going to be. Now, I do just have a quick little demonstration for this. So here I have a pendulum. I'm going to go back and pull that thing, and we could say, the period is going to be whatever it is. The one full swing, one full, out and back. So tick, tick, tick kind of along those lines. And as you can see, I can drop the mass down, I can raise the mass way up high, and the period is going to be whatever it's going to be. Now, the length is going to matter. The longer the length is, the slower it tends to go. The shorter it is, then the faster it's going to swing back and forth. So length matters and mass matters. Now, technically, gravity does matter as well, but the book doesn't talk about that, so I'm not going to. Now, I do still have these in there, as you saw in Physics 101. Suppose we had a pendulum that had a 1 meter long bob. It had a mass of 1 kilogram, and you replace it with a mass of 2 kilograms. Is the period going to change? No, the period does not depend on the mass of this thing. If, however, I tied this thing to a string that was 2 meters long, then what I've done is I've gone ahead and I've made it longer, and so the period should decrease. Scratch that. I said decrease, but I circled increase. That will actually increase because I've made it longer. Now, suppose I were to go ahead and take a pendulum and let this pendulum kind of wiggle back and forth in this plane just right there. And if I were to have a piece of paper, and I let that piece of paper kind of get drug along in this direction, and I were to just let some sand pour out of the tip of this thing, then all of a sudden, then I'm going to have my something wiggling in one-dimensional space and time, and then I have my second dimension right there. And since the mass doesn't matter, then it's not going to change the period. And what we're actually going to see is we're going to see this curve right there that's going to look a lot like a wave. And I'm actually going to go ahead and I'm going to call this a sine or a cosine. And this thing is going to be what we would call a wave. Okay, so now that we've introduced a wave, again, a wave is probably just going to be something that looks like a sine or a cosine. That's about as mathematical as we're going to get in Physics 101. Let's just get some jargon out of the way. Now, we could also go ahead and have a mass on a spring, and this is also going to be an oscillator just like a pendulum is. It's going to be a harmonic oscillator. And let's just get some jargon out of the way. When we talk about the peak-to-peak distance, we're actually going to call that the wavelength. Sometimes you're going to see the wavelength with the symbol of meters, or a symbol lambda, and of course it's going to have a unit of meters because it's a distance. We could also talk about the amplitude, and that's going to be this capital A, and it would also kind of be in meters. And it turns out that I could say it's a peak-to-peak distance. I could also say that the wavelength is the trough-to-trough distance. Essentially, it's just going to be the distance that it takes for one full oscillation to occur. We can also talk about the high points of the wave. We're going to call these guys crests. So the crests would be right here. And we could talk about the low points of the wave, and those guys are going to be these guys right there. We're just going to call those guys troughs. And I've already kind of said this already, but this kind of has it so you have everything in text. The amplitude is going to be the distance from the midpoint to the crest. So the midpoint is that dashed green line. So I'm going to call that guy the amplitude. And again, the wavelength is going to be the peak-to-peak distance, the crest to crest, the trough to trough, or even the midpoint to midpoint. So essentially just kind of remember one full up and one full down. Again, you may see this with the Greek symbol lambda whenever I shorthand it. Something else we can talk about when we talk about something that is vibrating or a wave is we could also talk about the frequency. And again, the unit tells you everything. The unit for frequency, it's going to have just a lowercase f. It's going to be a hertz. And a hertz is also going to be an inverse second. And I'm going to relate period and frequency here in just a little bit. So something with a period of 1 hertz is going up and down 1 times a second. Sound waves, we could be talking a few hundred hertz to a few thousand hertz. And when we talk about radio waves, we're talking about megahertz as well as possibly gigahertz. Now, you may remember metric prefixes. You may not have seen mega before. Mega is going to be 10 to the 6, and giga is going to be 10 to the 9th. So we are going to have some extra metric prefixes here. You probably remember, like centimeter, which was 10 to the minus 2, and kilometer. So you probably want to remember gigahertz and megahertz. And this just kind of says everything in text that I've already said already. A frequency is just going to be, the number of vibrations in a given time. And again, just pay attention. It's going to be a lowercase f, and it's going to have a unit of hertz. So if we had some 2 vibrations occurring in a second, and we're going to say that there are 2 vibrations per second, or we would say that something has a frequency of 2 hertz. Now, we can, of course, relate period and frequency, and it's pretty straightforward. Period is just going to be 1 over the frequency, and everything works out extremely well, because if you remember, period has a unit of seconds. This has a unit of inverse seconds, or hertz, and so when you flip that guy over, everything works out. Kind of the shorthand way to write that is going to be is going to say that period is going to be 1 divided by the frequency, and you could also just say that frequency is going to be equal to 1 divided by the period. Again, people sometimes confuse period and frequency. Just pay attention to the unit. Period is going to be in seconds. Frequency is going to be in hertz. So if we had a pendulum that was making 2 vibrations in 1 second, we would say it would have a frequency of 2 hertz, and it's going to have a period that would be 1 divided by 2, or it would be half of a second. So just a quick little practice here, and I do highly encourage you to give these a try before I solve them. Suppose you have something that with a frequency of 500 hertz. What is the period? So pretty straightforward. Period is going to be equal to 1 divided by the frequency. And when you go ahead and you type all this into your calculator, you're going to type in 1 divided by 500, and you're going to figure out that it has a period of 0.002 seconds. And just a little bit more practice, frequency of 20 hertz, then the period is going to be 1 divided by 20, so it's going to be 1/20th of a second. Now, something that is interesting about waves is what they transmit, is they actually transmit energy, but they do not necessarily have to transmit matter. And what I mean by that is, suppose I were to go ahead and take a rock, and I were to throw that rock right down here in the pond, then what's going to happen is if I had a piece of foam or something right over there, then that piece of foam is going to start going up and down because, well, it's receiving some energy. However, this water molecule that is right there does not move its way all the way over there to my piece of foam and make it move. So energy is being transmitted, but the actual water itself does not have to make the full journey. So kind of what's happening is the water is going up and down, and the wave is kind of going in the side-to-side direction. You could also say the same thing with air. You know, right now we have my voice coming out of your speakers. The air that is touching your speakers is not necessarily the same air that's touching your eardrum. Now, while we're on the subject of wave motion, the very last thing that I need to tie everything together is going to be how fast does the wave actually propagate? And this is going to be a really, really, really important equation. You're going to see it pretty much for the next couple of chapters, and you're going to see it again later in the semester when we talk about electromagnetic waves. It's pretty straightforward. We can relate wave speed to be related to frequency multiplied by the wavelength. And again, I always do like to shorthand this. We'd say speed is going to be equal to frequency multiplied by the wavelength. Now, the units do all work out. If you think about it, this is going to have a unit of a per second, and this should have a unit of meter, and we would expect our wave speed to be in meters per second, so everything kind of works out. So suppose we had a wave with a wavelength of 1 meter and a frequency of 1 hertz, then we would just say, okay, well, 1 times 1 is going to be a speed of 1 meter per second. So now let's just get a little bit of practice using this one. Suppose I have a wave, and I have a wavelength of 10 meters, so that tells me that this guy right here is 10 meters. Now you have to be careful. Is this the frequency, or is this the period? You take a look at the units, and you realize that that's actually the period. So the frequency is going to be equal to 1 divided by the period, so it's going to be 1 divided by 0.5. So the frequency is actually going to be 2 hertz. Now, pretty straightforward, we could figure out the wave speed is going to be equal to the wavelength, that's going to be the 10 meters, multiplied by the frequency, 2 hertz, and we're going to work our way out to answer number D.